Okay, welcome class. This video, we're still in chapter 3, we're working our way through. Our second topic is we want to be able to do some problems like this. We want to find the inflection points, which I have to tell you what that means, and intervals of concavity, which we have an idea for what that means, where it's concave up and where it's concave down, for an explicit function here. So they've given us something. We don't have to know what the graph of this looks like to go through the analysis, the calculus, that will give us an answer about concavity and intervals. But we will eventually use a tech tool to check our work to actually look at what this looks like. Okay, so in order to do this, we have a few pieces of information already. We know we're going to need which derivative. Well, the key word here, concavity, is your hint already that you know you're going to need the second derivative. So the only way to get to the second derivative is through the first. So we'll have to use the first derivative, then we'll get the second derivative. And then we need to understand inflection points. So before we start with an algorithm to solve this problem, step-by-step method to solve it, I need to tell you what an inflection point is. And that's pretty basic. An inflection point is also called an IP, just abbreviation for inflection point. And that's a point at which the function changes concavity. So it's just a place where you went from concave up to concave down or vice versa. So think about our classic example again, y equals x cubed, snakes through the origin. We said it was concave down from negative infinity to 0 and then concave up on the shaded part. So it switches concavity right here at 0. That is an inflection point. We're going to identify those on our graphs. They're kind of like critical points for the second derivative, places where you change concavity rather than changing from increasing to decreasing. Okay, so now that we know what inflection points are, we know what intervals of concavity are, we're going to start by getting our second derivative, and then I'll teach you the method that actually finds these IPs and tells you where you're concave up and concave down. Okay, but let's practice with our derivatives here. So there's a couple ways we could do this. Hopefully you see that there's like really two separate functions here. There's like, let me go put them in brackets. The first function is just x. The second function is x plus 1 squared. So one way to do this is with the product rule. First times derivative of the second plus the second times derivative of the first. It'd be a good idea to go ahead and practice that. Pause the video. Make sure you can do a product rule in this problem. But once you're done practicing that, make sure you got it. There's another way to do this that could be easier if you're pressed for time on a test, is what if we just factor this thing out? And then we'll just have some power rules, maybe constant rules, no problem, right? So it'll take a little bit of prep work before we do that. So if you're confident in your sort of pre-calculus work, that might be an avenue to go. Either way, we'll ultimately get to the same place. Even though the derivatives might look a little different, after simplification, they will be the same thing. So I'm going to do the second route, where we're going to factor this thing. So rather than taking the derivative, I'm really just massaging this function into a form that I think is going to be easier for me to take the derivative. So I'm rewriting it, and then I'm going to FOIL out x plus 1 times x plus 1. Maybe it's easier just to show you. That is right. So I'm just going to do this x plus 1 times x plus 1 and put it in parentheses here. That's going to be x squared plus an x plus an x. So x squared plus 2x plus 1. So not bad to do that. And then I'm going to distribute this x to each piece here. And then I'll get x cubed plus 2x squared plus x. Now I'm ready to take the derivative. That's still just f. The derivative then, now it's really nice, just some power rules, right? 3x squared plus 4x plus 1. But I don't stop there, because the question asked about inflection points and concavity, both of which have to do with the second derivative, so I'm going to need to take that. So f double prime of x is 6x plus 4. Okay, now I'm ready, once I have all these pieces, to tell you about the algorithm, to find out where it's concave up and where it's concave down. This is very similar to something we've already done. It's almost like an extension or level up from that. So remember, we'll put it over here again, that we did stuff with an F prime line where we put CPs on there. Maybe we had two CPs, CP1 and CP2. And we plugged things in from every interval. That's divided into 3 intervals. We picked a test point and plugged it into F prime. And we saw whether we were in, like if we had a positive, negative, positive, that told us we were increasing on the interval from negative infinity to CP1. We were decreasing because a negative first derivative tells you your function is decreasing, and then we were increasing, right? We're gonna do something very, very similar, but we're gonna plug into the first derivative, instead of F prime, we're gonna do the same thing, but with F double prime. And we'll see why that makes sense. But instead of putting CPs, places where the first derivative is 0, we're gonna put what are called PIPs. PIP stands for possible inflection point. And that's a place where the second derivative is equal to 0. So we're going to do just like we do with CPs, but we're doing it with the second derivative. I'm going to take the second derivative, set it to 0, solve this equation, and I'll get a PIP at x equals what? Minus 2/3? 4/6 is 2/3. So minus 2/3 solves this linear equation. This is a possible inflection point. It's a place where I might change concavity from concave up to concave down, or concave down to concave up. If I do change concavity, we erase the first P and say it's actually an inflection point. Right now, it's just a possible. So we take every PIP we get, and we put it on an F double prime line. There's only one PIP, minus 2/3. Had you had more, you'd fill in more of them. You take those and put them on your F double prime line, and now this divides it, in this case, into 2 intervals. I pick a point from each interval. So I try something to the left of negative 2/3, maybe like F double prime of -1, and maybe F double prime of +1. Just making the numbers easy to plug in. And I'm checking, is my second derivative positive or negative? So let's see, when we plug in F double prime of -1, so F double prime of -1 says wherever I see an X, I stick a -1. So I'll get -2. I don't really care that there's the 2 there, I care that it's negative. Now what does that negative sign mean? If your second derivative is negative, think back to the first video, pause it or look back in your notes. In the beginning of the journal, chapter 3, it says if your second derivative is negative, your function is concave down there. And it wouldn't matter which point I picked. I picked -1, just like over here. Pick any point. I could have tried -2. Plug in -2. You'll see the same thing happens. You still get a negative number. I'll get -8, -3, and you just keep any point you would pick. So that's why we only have to pick 1. And when I plug in the +1, I get a positive number. When your second derivative is positive, that means your function is increasing. No, that's on your first derivative. When your second derivative is positive, it means your function is concave up. Okay, so we have every piece of information from this little sign chart. This right here tells you everything you need to know to answer this question. The F double prime line, we're going to call it, makes a sign chart that has all the information we need. What can we say about this PIP? This was the PIP at -2/3. Is it an actual IP? Can we erase that first P? Yeah, it changes from concave down to concave up. So it gets an upgrade. It's actually an inflection point. And then we can give the intervals. So find the inflection point. We have an inflection point at x equals -2/3. And then the intervals of concavity. So our answer would be that it's concave up on the interval from -2/3 to infinity. It's concave down on the interval from -infinity to -2/3. Now, that was for this sign chart. But let's just not have an explicit example, but suppose we had a different sign chart. So suppose this is a different example. I'm not telling you what the f of x is for now, it's just something. And suppose your f double prime line turned out like this. Suppose we had actually 3 PIPs. And we'll put them in order. Say we had -4, 1, and 5, and they're all PIPs, which means I took the second derivative, whatever it was, set it to 0, and I got -4, x equals 1, and x equals 5. And then suppose when I picked a point, I got plus, plus, minus, plus. How do you interpret this? So again, make sure you remember that this is f double prime. So the second derivative tells you about concavity. Don't be tempted, some of you will, to say, oh, it's increasing, it's increasing, it's decreasing, it's increasing. No, that will be the case if you were doing an f prime line. We have an f double prime, so we know the interval of concavity would be its concave up from -infinity all the way through to 1. And it's also concave up from 5 to infinity. It's concave down in this little stretch here from 1 to 5. We can also say that these PIPs here, this still is a possible inflection point. It didn't actually change. This one is an actual inflection point and an actual inflection point. So making sure you can interpret that once you do the analysis and the arithmetic, I guess, algebra and arithmetic, to fill in this f double prime and then interpret it correctly. All right, we're gonna do one more. We got time to do one more example. Let's do a little bit tougher one. Same sort of question though, change the function. Find the intervals of concavity and the inflection points, if any exist. I mean, you don't necessarily have inflection points for every function. Or let's do something that uses some more rules. Let's try x e to the x. This way we'll get to practice some more of our differentiation rules. It's always good to make sure you've got those down. Okay, so the key thing here is that you see some key words for you. Concavity, inflection point, you think second derivative. Okay, so I'm going to need the first derivative. What do you notice about this function? What kind of differentiation rules are you going to need? Pause the video, take a minute, and just sit there with this function and say, which rules do you think you need? What first thing I look at it, I see that I actually have two functions multiplied by each other. So I know I'm going to need the product rule, and then somewhere inside that product rule, I'm going to need the e to the power rule. So starting with the product rule, the structure of it, first times derivative of the second plus the second times derivative of the first. Fill in the copying boxes. So this is our first function, this is our second function. So x goes here, e to the x goes there. Then I fill in my derivative boxes. The derivative of e to the x, that's e to the power. It's e to the power times the derivative of the power. So e to the x times 1, which is just e to the x. And then the derivative of x is just 1 by the linear rule. So this is x e to the x plus e to the x. I can leave it that way and take another derivative because I need to get to the second derivative. Or I could factor. Either way, it's just as easy to do, whether I stopped at this line and took a derivative or this line. One advantage of this line, though, is it didn't ask us this, but maybe just to review. Suppose it asks to find the CPs and intervals of increase and decrease and all this other stuff. So I would stop here to answer CPs and intervals of increase and decrease, because those are keywords that tell me about the first derivative. Whereas inflection point and concavity are keywords that tell me about the second derivative. So to answer the first part, CPs and intervals of increase and decrease, I'd stop here with my first derivative and set it to 0 to find CPs. What already is nicely factored. E to the x equals 0, what do you remember about that? Pause the video, go back to your notes, maybe remember it right off the top of your head. E to the x equals 0 has no solution because ln of 0 doesn't exist, doesn't make sense. So e to the anything equals 0 is no solution. So e to the x equals 0, don't even have to worry about it. x plus 1 equals 0. That's easy. We get a CP at x equal minus 1. So we've answered the first question. There's a CP at x equals minus 1. The second part, intervals of increase and decrease. Those happen on an F prime line. You take all your CPs. Oh, nice, I only got one. Divides this into two intervals. I pick a point from each interval. I plug, say, -2 into the first derivative. So I'm going to get f prime of -2. That's e to the -2 times -2 plus 1 is -1. E to the anything is positive. Check it out on your calculator. A positive times a negative is a negative. That negative is different than the second derivative negative. That means the function is decreasing. So I can start answering about decrease. We can say the interval of decrease is from -infinity to -1. And then we'll figure out what happens on the second interval. To figure that out, I pick a point from the test interval. Maybe I try 0. That'd be an easy one to try. E to the 0 is 1 times 0 plus 1 is 1. So 1 times 1 is 1. That's positive. That means the function is increasing. So it's increasing from -1 to infinity. All right, so now we're ready to do the second derivative. Let's get this scrap work out of here. And we'll do the second half of this problem now. Inflection points and intervals with concavity. I need to take the second derivative. The way it's written here, it's easy to see that this is a product rule with a first function and a second function. So I get to practice one more time my product rule and my e to the powers. It's first times derivative of the second plus second times derivative of the first. First function, e to the x. Second function, x plus 1. The derivative of e to the x goes here, which is just e to the x. The derivative of x plus 1 goes here, which is 1. Oh, I did that backwards, didn't I? 2 prime. 1 prime. I mixed those two up. So the derivative of x plus 1 goes here. Sorry, that's 1. And then back here is e to the x. All right, looks better. Again, we can leave it like that, but it makes sense to try to do a little work to simplify because ultimately we want to set this thing to 0. So let's do another line where we have e to the x plus x. I'm going to distribute this. That's x e to the x plus e to the x. All right, now I want to set that to 0. Find what values of x make that true. That is an exponential equation. There's no hope for just guessing a number and solving that. But what you could do is see if there's anything you can factor. I've got one term, a plus sign, another term, a plus sign, another term. Is there something that's common to those 3 terms? Yeah, there's an e to the x in each of them. So let me factor it out. I'll be left with 1 plus x plus 1 equals 0. So I'll have e to the x plus 2 equals 0. Now this is something that's easier because 2 factors multiplied together equals 0. The only way that can happen is because this is a special 0 on this side. The rule of 0 is that each factor is 0. So I can set each one to 0. E to the x equals 0 and x plus 2 equals 0. E to the anything equals 0 has no solution. This one has a solution x equals -2. And what is that? Is that a CP, a PIP, or an IP? At this point, because it's the second derivative equals 0, it's just a PIP. So I still can't answer the thing about inflection points yet. I'm almost there though, because what I can do is make my F double prime line. I put all my PIPs on there. There's only one, that makes it easy. That divides this into 2 intervals. I pick a point from each interval, plug into the second derivative. So I'll try like -3 over here. So which line, maybe this line here is the easiest to plug in. It's already simplified. You can plug in at this line or this line or this line. They're all the second derivative. Just makes it a little bit easier to plug into the simplified part. I'm going to try -3. That's going to be e to the -3, which is a positive number, times -3 plus 2, which is a negative number. Negative times a positive is a negative. So this means we're concave down because I did with the second derivative. And let's do one more. We have to plug in, say, 0. F double prime of 0 is e to the 0, which is 1, which is positive, times 0 plus 2 is 2, which is positive. Positive times positive is positive. I plugged into the second derivative, so that tells me information about concavity. So we change from concave down to concave up. That means this PIP is an actual IP. So I can answer that the inflection point at x equals -2. And then the intervals of concave up and concave down, I say we're concave up from -2 to infinity, and we're concave down from -infinity to -2. Okay, but that was, 5-10 minutes of work, a couple of whiteboards full of work. After we've done it, it's a good idea to check your work. And you can do that with a tech tool or a calculator. I encourage you to do that. So a couple tech tools, I'm going to share my screen. We've already talked about how you can do this with Google. Just enter y equals. The original function was x, e to the x. Yeah, there's some graphs down here, but I think I really like Desmos a bit better, and maybe you guys will too. You're probably more familiar with that. Maybe a high school teacher used Desmos in their graphing calculator. And we'd enter y equals x, e to the x. All right, so we have this shape. And let's check some of our points on there. So we said that we found a critical point at -1, so that would be here. And if you zoom in a bit, it does look like the graph levels out at -1, right? And it has a horizontal tangent line there. So we found that precisely rather than just having to guess. We said that's exactly the place where your slope is 0 at -1. And then at -2, we say that's an actual inflection point because you change concavity. So let's take a look at the concavity. We found the concavity interval from -infinity, so starting here, we said all the way up to -2, you're concave down. Yeah, it looks like part of a frown. And then at -2, it's saying it's switching to part of a smile. All the way to the rest to infinity, it does. Then the last thing we found were the intervals of increase and decrease. We said you're decreasing from -infinity to -1. So I'd be pedaling down here, just coasting all the way up to -1. Yes, that's true. And then it's uphill, and whoa, that's steep uphill, Tour de France stuff, from -1 to infinity. Yeah, so all that checks. Again, that's always a good idea once you've done the calculus and the algebra to check your work visually. And it's also a good way to, before you start a problem, to get a sense of what's happening, but you have to show your work. You have to show us your calculus that you do match what you see visually. And we'll see why it's important to be able to do the calculus, because there are some problems for which you can't visualize them. And we'll get to those eventually. All right, have fun with concavity intervals in the second derivative, F double prime line, double prime.